Hey there, and welcome. Today we're going to look at mathematical functions a little differently. Not just as some static formula on a page, but as living, breathing things that have their own behaviors and, as we'll find out, a hidden superpower we can unlock.
So let's just jump right in with the big question that's going to drive everything we talk about today. If a function takes a number, does something to it, and spits out a new number, can we go backwards? Can we build a machine that takes that output and perfectly returns the exact number we started with? Can we undo it? That's the puzzle we're going to solve.
And here's our plan. We'll start by just watching how a function moves. Then we'll see how that movement gives it a really unique property. That property, well, it's the key that unlocks its power to be reversed. And we'll wrap things up by looking at the incredible visual connection between a function and its undo button.
Okay, first up, the behavior of a function. It all boils down to a pretty simple observation you can make just by looking at a graph. As you move your eyes from left to right, is the line always going uphill, or is it always going downhill? This simple commitment to one direction is what we mean by its behavior.
So here's the formal breakdown. For a strictly increasing function, bigger inputs give you bigger outputs. As x goes up, y goes up. Simple enough. But for a strictly decreasing one, as you move to the right, the graph always goes down. Bigger inputs give you smaller outputs. See how that little inequality sign flips? That's the mathematical signature right there, the telltale sign of a downhill ride.
And yeah, there's a fancy name for this kind of steady, predictable behavior. We call it strictly monotonic. You can think of it like a train on a track that can only go forward or only go backward, but it can never make a U-turn. It's committed to one direction for its entire journey. And that single-mindedness, well, it turns out to be a huge deal.
So, what's the payoff for being so predictable? What special prize does a function get for never, ever changing its direction?
Well, think about it for a second. If a graph is always climbing, it can't dip back down to a height it's already visited, right? And if it's always falling, it can't rise back up to a previous level. This really simple visual idea has a pretty profound consequence.
It earns this special badge. It's called a one-to-one function, and this is basically a guarantee. It means that every single output, every y value, is linked to one and only one input. No two different starting points will ever land you at the same destination. No duplicates allowed.
And this gives us a super easy visual trick to check for this property. It's called the horizontal line test. Just imagine sliding a ruler horizontally up and down the graph. If that ruler never ever touches the curve in more than one spot at a time, boom, you've got a one-to-one function.
And this, right here, this is the main event. That strict, predictable, monotonic behavior we saw, it guarantees the function will be one-to-one. It's always going to pass the horizontal line test. But, and this is a big but, you can be one-to-one without being monotonic.
And this picture shows that perfectly. This function totally passes the horizontal line test, right? No horizontal line hits it more than once. So it is one-to-one, but it's obviously not monotonic. It goes down for a while, and then, bam, it jumps and starts going up. So this is super important. Being predictable is enough to get you this property, but it's not the only way.
Okay, so we've spent all this time on this special one-to-one property. So what? Why do we care so much? Well, because being one-to-one is the golden ticket. It's the key that unlocks that secret power we talked about right at the start, the ability to be perfectly undone.
This is the absolute rule of the game. A function gets an inverse, a perfect reversal machine, if and only if it is one-to-one. That guarantee of no duplicates is what lets us trace our steps backward from an output and know for sure which input it came from. Without that, the whole idea of reversing it just falls apart.
And this is what we call the inverse function. You'll see it written as f with a little -1 up top. It is quite literally the ultimate undo button. If the original function f takes x to y, the inverse function, f inverse, takes y right back to x. The roles of input and output are completely swapped.
All right, so we know if a function is one-to-one, this inverse exists. But how do we actually find it? How do we get the formula for it? Well, luckily, there's a pretty straightforward recipe we can follow.
Here it is, the three-step plan. First, you gotta prove it's one-to-one in the first place, or you can't even start. Second, you just replace the f of x part with a y. And third, you roll up your sleeves and use your algebra skills to rearrange the whole thing and get x by itself. What you're left with, that's the formula for your inverse.
Now, before we get to the cool visuals, let's look at a really practical use for all this theory. I mean, how on earth can knowing about monotonic functions help us solve an equation that looks, well, honestly, kind of impossible to solve algebraically, like this one?
Check out how powerful this is. First, we just move everything to one side to get a function that equals 0. Now here's the magic step. We prove that this function is strictly increasing. That means it has to be 1-to-1. And because it's 1-to-1, its graph can only cross the x-axis once. Tops. So if we can find just one solution by, well, just looking at it, and it's pretty easy to see that plugging in x equals 0 works, then we know with absolute certainty that it is the only solution. Game over. We don't have to look for any others. That's a massive shortcut.
Okay, time for the final piece of the puzzle. What does this deep connection between a function and its inverse actually look like? It turns out there is a stunningly simple and beautiful picture that tells the whole story.
And here it is. Their graphs are perfect reflections of one another. And the mirror? It's just that simple diagonal line, y equals x. If you could somehow fold the graph paper right along that line, the function's curve would land perfectly on top of its inverse's curve. It's a perfect match.
And the logic for why this works flows directly from what an inverse is. Look, if the point alpha comma beta is on the first graph, that just means f of alpha equals beta. But by the very definition of an inverse, that means f inverse of beta must equal alpha. So the point with the coordinates flipped, beta comma alpha, has to be on the inverse's graph. And those 2 points, alpha comma beta and beta comma alpha, are always perfect mirror images across the line y equals x.
So you see, this relationship isn't just some abstract algebra trick. It is a fundamental, beautiful symmetry that's woven right into the geometry of these functions. The inverse isn't just an undo button, it's the function's twin in the mirror. And that leaves us with one last, kind of mind-bending question to chew on. We've seen that the inverse is a function's mirror image, but what happens if a function is its own mirror image? What if its graph already has perfect symmetry across that y equals x line? What does that reveal about the very special relationship that function must have with itself?